Hey good people, welcome back. In this video, we're going to learn how to find limits analytically, aka algebraically. Something that you can do to help better understand this is to look at these notes in addition to watching this video. And if you really want an in-depth analysis of limits, you could read the section in the calculus textbook. I uploaded these two PDF files along with this video in the Google Classroom post. In this video, we're going to look at three different methods for finding limits analytically. The first method we're going to look at is called direct substitution. And this is when the functions are continuous. You could just directly substitute whatever number you're finding x is approaching to, substitute that number into the function and evaluate it. We're going to do two examples of that with polynomial functions and two examples with trigonometric functions. The other method is called factoring or dividing out technique. This is when you have a rational function and you factor the numerator and denominator and find that there's a common factor that exists in both the numerator and the denominator, and you can cancel that out, and then you can find what the limit approaches. The final method we're going to do is called rationalizing, and this is when you multiply by the conjugate of a binomial to get rid of a radical. And we're going to see two examples of that. So let's get started. Here's an easy one where we're just going to use direct substitution. Find the limit of the function x cubed minus 2x plus 3 as x approaches 2. Well, since this is a continuous function, we can simply replace x with 2. Just going to evaluate this function by substituting x with a 2. And I get 8 plus 4 plus 3, which is 12 plus 3, which is 15. So the limit of the function x cubed minus 2x plus 3 as x approaches 2 is equal to 15. Another continuous one where we can use direct substitution. Find the limit of the function x cubed minus x plus 5 as x approaches 6. X cubed minus x plus 5 as x approaches 6. I'm going to just simply replace x with a 6. So we have 6 cubed, which I think is 216, but let me check. Yep, 216. So 216 take away 6 is 210, plus 5 is 215. Alright, so the limit of the function x cubed minus x plus 5 as x approaches 6 is equal to 215. Alright, let's do a direct substitution with the trigonometric function. Now, to do this on the calculator, you want to make sure you're in radian mode. So I have my calculator set to radian mode. And since we know that the function sine is continuous for all values of x, it just keeps oscillating like this. We could just plug in 5. We know it's going to be defined at 5 pi over 6 radians. So I'm just going to do sine of 5 pi over 6 radians. And that is equal to 1/2. Now, another way you can get the same answer is by looking back at our special right triangles, or perhaps the unit circle that we constructed based on those special triangles. If you want to find 5 pi over 6 radians, because we're replacing x with 5, so we have 5 pi over 6 radians. That would be right here. And what we can do is just look for the sine. Remember, the sine, we would look at the that y coordinate right here, and that equals 1/2. So our answer is 1/2. All right, let's do another trig problem. Find the limit of the function cosine of pi x over 12 as x approaches 2. Since this involves pi, we're going to assume that we're working in radians. Cosine is another continuous function. It oscillates between -1 and 1 like this. And we're looking at 2 pi over 12 radians. So we're replacing x with a 2. And if you reduce that, this is going to actually be 1/6, right? 2 over 12 reduces to 1/6, so this is pi over 6. All right, let's find pi over 6 on our unit circle. So this is equal to cosine of pi over 6. That would be right here. And when we're doing cosine, we're looking for the x-coordinate. So this is root 3 over 2. Our answer is equal to square root of 3 over 2. And we could verify that with our calculator. I'm just going to do cosine of, I'll type it in here how it was originally written, pi multiplied by x, and x was approaching 2, over 12. And we should get this root 3 over 2 as our answer. Now square root 3 is 1.73 something, and if you divide that by 2 you get 0.866. So this does verify that. Just to show you again, square root 3 over 2 is in fact equal to that. Alright, now let's do one where we have to do a little bit of algebraic trickery. This is the dividing out technique. If we were to use direct substitution here, we'd run into a little trouble. We have x squared minus 9 over x minus 3. If I were to directly substitute 3 for x, I'm going to get an error because you can't divide by 0. This is going to equal 0 over 0 when I substitute 3 in for x, and this is called an indeterminate form. 0 over 0 is an indeterminate form. We don't really know what the limit equals yet when we get 0 over 0. The limit might not even exist. There could be an asymptote. It could approach infinity, or perhaps it approaches negative infinity from one side and approaches positive infinity from the other. So to do a little further investigation, we like to factor these. So we're going to factor the numerator and the denominator and see if we can gain some further insight. Notice the numerator is the difference of two squares, and that can be factored as x minus 3 multiplied by x plus 3. The denominator of x minus 3. We know that x is not equal to 3, it's approaching 3. So we can say that this can cancel out because we're assuming we're getting closer and closer to 3 without ever reaching it. So we don't run into the issue where x is equal to 3 and we have dividing by 0. So we can just cancel that out because this is a limit as x approaches 3. We know that x is not equal to 3. Alright, so we really have to find the limit as x approaches 3 of this function here, which can be solved via direct substitution. The limit of x approaches 3 of this, we can just directly substitute in 3, and 3 plus 3 is 6. So this is going to equal 6. So the limit as x approaches 3 of x squared minus 9 over x minus 3 is equal to 6. And just to verify that, what I'd like to do is just look at the graph of this function. So I'm going to just type it in exactly how it's written here. It's x squared minus 9 over x minus 3. As we get really close to 3 from each side, this should approach 6. Let's look at the graph. I'm going to have to change my zoom window. So as I get close to 3, this y value gets close to 6. You can kind of see that from this cursor here. Another way you could look at that is by looking at the table. As we get really close to 3, well, 3 gives you an error, but as you get close to 3, I'm going to change my delta x to like 0.01. You could see that on both sides of the number 3, you're getting really close to 6. It's approaching 6 from the right, and it's approaching 6 from the left. So we just really verified that this limit is equal to 6. Another one where we use the dividing out technique. Okay, so if I were to do this using direct substitution, we would definitely run into an error. I'd have 9 minus, or I would plug in 3, and I'd have 9 minus 9 is equal to 0. I would plug in 3 here, and I would have 9 plus 6 minus 15. 9 plus 6 is 15 minus 15. That's equal to 0. Another indeterminate form. This is our 0 divided by 0, and we don't really know what the limit equals yet. There might not even be a limit. This could approach infinity, or it could approach infinity and negative infinity. We don't know what this is yet. So what we're going to do is factor it and divide out. The factor both the numerator and the denominator in this one. The numerator is the same as our previous problem. It's a difference of two squares. X minus 3 and x plus 3 will factor that. And then the denominator, we need to find two numbers that multiply to negative 15 and add up to positive 2. Well, those two numbers are negative 3 and positive 5. You could verify by using the distributive property that this does, in fact, multiply out to x squared plus 2x minus 15. Notice we have a common factor in both the numerator and the denominator. We can cancel that out. And we have the limit of the function x plus 3 over x plus 5 as x approaches 3. What does that equal? Let's find out. We can use direct substitution here. So we're just going to directly substitute 3 for x. We're allowed to do that because we don't have any 0 in the denominator or anything like that. So I'm just going to replace x with 3. And I get 3 plus 3 is 6. 5 plus 3 is 8. 6 divided by 8. So this is equal to 3/4 or 0.75. So the limit of the function x squared minus 9 divided by x squared plus 2x minus 15 as x approaches 3 is equal to 0.75 or 3/4 if you write it as a fraction. We could verify that with our calculator. I'm just going to do that real quick. So this is x squared plus 2x minus 15. We're going to approach 3 from both sides. We can see that this is getting pretty close to 0.75 from the left side, and it's approaching 0.75 from the right side. So we just verified our work is correct. So it is approaching 3/4. All right, let's do one where we have to use that other, one more dividing out technique. So I did 3 examples of this. So the first example, the degree of the denominator was less than that of the numerator. In this example, they were equal. And in this example, the degree of the denominator is greater than that of the numerator. So we'll do one more dividing out example. All right, if I were to directly substitute 6 in for x, what would happen? 6 goes here. 24 minus 24 is 0. 6 goes here. I would have 36 minus 24 is 12, minus 12 again is 0. That's an indeterminate form. So we're going to have to use dividing out to figure out what this limit approaches. The limit of the function 4x minus 24 over x squared minus 4x minus 12 as x approaches 6. Let's factor out the GCD from 4x and 24. That would be the number 4. 4 goes into both of those terms evenly. 4 times x is 4x, and 4 times negative 6 is negative 24. In the denominator, we have a trinomial, so we're looking for two numbers that multiply to negative 12 and add up to negative 4. those two numbers that multiply to -12 and add up to -4, -6 and +2. All right, now we can cancel out this common binomial factor of x minus 6, and we have the limit of the function 4 over x plus 2 as x approaches 6. This can be solved with direct substitution. We're just going to directly substitute in a 6 for x. We have 4 divided by 6 plus 2 is 8, so this is equal to 1/2 or 0.5. And I can verify that on my calculator just to check my work. So I'm doing 4x minus 24 in the numerator, in the denominator x squared minus 4x minus 12. And as x approaches 6, so I'm going to have to go in my table all the way to 6, and I'm not going to count that way. So there's a little trick. If you go in the table set, you can tell you where to start in the table, so I'm just going to say start at 6. And as x approaches 6, from both sides, from the right side of 6, it approaches 0.499, so it's getting close to 0.5. And from the left side of 6, it's approaching 0.501, 500. It's getting really close to 0.5. So we verified that this is in fact equal to 1/2. So the limit of the function 4x minus 24 over x squared minus 4x minus 12 as x approaches 6 is equal to 0.5 or 1/2. All right, in this next problem, we're going to again begin by trying to find the limit by direct substitution. Let's see what happens when I try to directly substitute in 4. We have in the numerator 4 times 4 is 16, minus 16 is 0. In the denominator, we have 4 minus 3 is 1. The square root of 1 is 1, and 1 minus 1 is 0. So this is another indeterminate form. And we're going to have to use a different technique this time because we don't know anything about factoring radicals. So this technique is called multiplying by the conjugate. The conjugate of a binomial is the identical binomial except you separate the two terms with the opposite sign. So we're going to take that denominator, the x minus 3, the square root of x minus 3 minus 1, and the conjugate of that is the same thing but with a plus in front of the 1. We're going to multiply by that on the numerator and the denominator. And the reason we're allowed to do that is because whenever you multiply by something in the numerator and the denominator, you're basically multiplying the whole thing by 1 because anything divided by itself is equal to 1. And you're allowed to multiply anything by 1. It doesn't change it. So I'm going to multiply both the numerator and the denominator by the conjugate of this thing right here. Conjugate of square root x minus 3 minus 1 is the square root of x minus 3 plus 1. And the reason we're doing this is because it's going to make that radical go away in the denominator. So this technique is called rationalizing because we're attempting to change this radical answer into a rational answer. All right, so you don't want to just cancel out what we just did. That would kind of defeat the purpose. But you try to look for something that you can cancel out. So let's try to first FOIL the denominator. First, outer, inner, last. And then we'll see if this cleans up a little bit. I'm just going to leave the numerator how it looks right now without foiling it yet. Sometimes you can get lucky and you don't have to actually multiply them. You can find something that will cancel out. Alright, so the x minus 3, the square root of x minus 3 multiplied by the square root of x minus 3, well, the square root of something multiplied by itself, it just gets rid of the square root. So we're really just left with x minus 3. And then the outside times the outside, 1 times x minus 3 is just 1 times the square root of x minus 3 is the square root of x minus 3. And then negative 1 times the square root of x minus 3 is negative square root of x minus 3. And then over here, negative 1 times 1 is negative 1. Notice those two middle terms are identical but opposite in sign. They cancel one another out. I'm going to rewrite this over here, kind of cleaning it up a little bit. So the limit of the function 4x minus 16 multiplied by the quantity the square root of x minus 3 plus 1 divided by this canceled out. We have x minus 3 minus 1. Oh, x minus 3 minus 1, that is x minus 4. So in the denominator, we just have x minus 4 now. That cleaned up nicely. And in the numerator, there is sort of an x minus 4 right here. You can factor out a 4 from that 4x minus 16, and you're going to be left with x minus 4 in parentheses. And then we have the square root of x minus 3 plus 1. So this does have some canceling that we can make use of. So I don't actually have to multiply the numerator out. This is going to cancel with this. And we're able to do that because x is approaching 4. It's not equal to 4. So the limit of this function, 4 multiplied by the quantity square root x minus 3 plus 1, as x approaches 4, we can solve this by using direct substitution. I'm just going to substitute 4 in for x. 4 minus 3 is equal to 1. So we have, let me get a little bit more space here. The limit of the function 4 multiplied by the quantity x minus 3 square root of x minus 3 plus 1 as x approaches 4. So I'm just going to replace my x with a 4. And now I can just solve this by using direct substitution. So I have, this is equal to 4 times square root of 1 plus 1. That would be 4 times 1 plus 1, which is 4 times 2, which is equal to 8. So this limit is equal to 8. And I was able to get rid of the radical in the denominator by multiplying by this thing, which is called the conjugate. And I just want to verify that I'm correct. So I'm going to go into my calculator and type in this function in my y equals, and then check the table as x approaches 4. So as you see, as we're getting closer to 4 from the left side, it's getting close to 8, 7.93, 7.95, 7.97. And as we get close to 4 from the right side of 4, it's getting closer and closer to 8 also. 8.05, 8.03, 8.02. So we could see that it is, in fact, approaching 8. So we checked our work. All right, let's do another one of these problems where we have to multiply by the conjugate in order to get rid of the radical expression. So we'd like to begin these just by first seeing if we can do it easily by direct substitution. I'm going to directly substitute 4 in for x and see if I could find the limit that way. In the numerator, 4 plus 5 is 9. The square root of 9 is 3. 3 minus 3 is equal to 0. In the denominator, 4 minus 4 is 0. So we have 0 over 0 again, another indeterminate form. So we can't solve this via direct substitution. We're going to use that multiplying by the conjugate of the radical expression technique. This is what the book calls rationalizing it, and I guess they call it rationalizing it is because this is an irrational expression here, this involving a radical, and we're going to try to turn it into a rational number in the numerator. We're going to try to get rid of that radical. The way that we get rid of it is by basically multiplying it by its conjugate, and the conjugate is the identical expression except you separate it with the opposite sign. So I'm doing the square root of x plus 5. Instead of minus 3, it's plus 3. And I have to do that on both the numerator and the denominator, or else I'm actually changing this original function. Now, because I have the same thing here and here, it's essentially like I'm multiplying by 1, and you're allowed to multiply anything by 1 without changing it, and that's why you're allowed to do this. So we're going to FOIL this first times first, outer times outer, inner times inner, and then last times last. So we have this thing multiplied by itself. Well, the square root of a number times itself is equal to that number. So the square root of x plus 5 times the square root of x plus 5 is just x plus 5. And then 3 times the square root of x plus 5 is just 3 times the square root of x plus 5. And then we have negative 3 times the square root of x plus 5. So that's negative 3 times the square root of x plus 5. And then finally we have negative 3 times 3, which is negative 9. We're going to leave the numerator we're going to leave the denominator as it looks. We're not going to mess with that just yet. I'm just going to leave it as the quantity x minus 4 multiplied by the quantity the square root of x minus, or x plus 5 plus 3. We can clean up the numerator quite a bit. We have these two are identical but opposite in sign. They cancel one another out. And then we just have to combine our 5 with our negative 9. And 5 minus 9 is negative 4. So we do have an x minus 4 that can be canceled in both the numerator and the denominator. And we're going to go ahead and cancel that out. And this is equal to 1 over the square root of x plus 5 plus 3. And this is actually something we can solve via direct substitution. So I'm just going to directly substitute 4 for x to get my limit here. So the limit of the function 1 over the square root of x plus 5 plus 3 as x approaches 4. What does that equal? Well, we have the square root of 4 plus 5, which is the square root of 9. And the square root of 9, of course, is equal to 3. So we have 3 plus 3 in the denominator. That's 6. So the limit is equal to 1/6. All right. So just to verify that here on my calculator screen, I typed in my function, and I go to my table, and I find the limit by looking as x approaches 4 from both the left side and the right side. As we approach from the left side, you can see it's getting close to 0.166, 1667. We're getting closer and closer to 0.16 repeating. And 0.16 repeating is equal to 1/6. Okay, so thank you for watching the video. The assignment this week is actually due next Friday. So there's I guess there's like about 12 or 13 questions, but we're going to be able to meet up 2 times before this is even due. So we'll be able to talk about this, ask some questions, and I'm going to also upload a few Khan Academy links to this topic that will come on Wednesday. Thank you again for watching, and I look forward to seeing you in our video meeting.